Okay, good morning, everyone. Good morning, guys. Anyone, please answer. Do you guys hear my voice?
Yeah, can hear.
All right, thank you. Okay, I'm going to share my screen. Okay, I hope that you guys can see my screen. Okay, so for today, we will go for our third tutorial. This is our third tutorial for Fundamental of Electronics. Okay, this is our final class lah. Okay. And for today, we will go for FET transistor circuit. This session will be recorded. I will share the link in WhatsApp group later. Okay. And before we end these sessions, I would like to, we will have some short discussion on cost assessment 2 and also for the uh, final exam. Okay. Please remind me if I forget to discuss on that two things. Okay, so let's get started. Is in previous class we have covered for the, I hope that you guys still remember what we have learned in previous class. First, tutorial 1 is on the PN junction, semiconductor and diode. And then for the tutorial 2, we have covered on the BJT, bipolar junction transistor. Okay, and in tutorial 3 today, we will learn about the FET circuit, field effect transistor, okay, which are mainly designed as a small signal amplifier with different configuration, which also involve with the junction field effect transistor, JFET, and also the MOSFET, metal oxide field effect transistor. Okay, and for the JFET, it is also designed for, we have common source, common gate, and common drain. The second objective here, we have common source, common gate, and common drain, and we will see the effect of the AC voltage gain by the output impedance and also the source resistance. Okay, next one we will discuss on how to design the MOSFET for common source and also drain feedback configurations, include with the DC and AC analysis. And also in final part, we will discuss on low frequency and high frequency response for small signal amplifier due to the capacitors that we have in the circuit, which are the bypass and also the decoupling capacitors. Okay, that one will cover on the frequency response. This one, okay, and also we will discuss on the 3 dB AC voltage gain, which we have conduct in our experiment last week. Okay, what is the meaning of the minus 3 dB gain? All right. Okay, for small signal model, please, if my voice is not clear or the screen is, I'm not sharing my screen, please inform, yeah. Okay, so what is actually small signal analysis? Okay, small signal model, it is for small signal analysis. We carry out a non-linear element. For the transistor, it is actually non-linear element. It is either BJT, FET, or the MOSFET. And then we want to replace with the linear element. Linear element is the RLC, resistor, inductor, or the capacitor. Okay. All right, this is objective for this, the first subtopic. Okay, for the model of the small signal of the FET based on the mid-range frequency with several assumptions to be made. And then we show model for the small signal amplifier. And this is as the assumption. Okay, assume that the amplifier is operating in mid-range frequency with the external bypass and decoupling capacitors of the circuit, and internal capacitance of the transistor have no effect. Okay, the internal capacitance, it is actually depends on what are the types of transistor that we use. If we use the FET, FET will have the, this is for FET, okay, gate, source, and the drain. So we have the CGD, we have the CDS, and the CSG. Okay, so this is the internal capacitance. If we use the BJT, the internal capacitance, I hope that you can still remember for the BJT, okay, um, base, collector, and emitter. So we have the CCE, CBE, and then CCB. In between each one, here internal of the transistor, we have the capacitor. That is why we call it as internal capacitance. For example, for this one, we have this one capacitor over there. And at each of the kaki dia ni, each of the terminal, we have the capacitance. Okay. And what is the bypass capacitor here? Okay. For the bypass capacitor, this is the capacitor that short the AC signal to the ground. Okay, that one we call it as the coupling and decoupling capacitor. Okay, we use to couple and cascade the electrical network with one network. Basically, it is located at the either input or the output, or in between two stages of the network of the circuit. If we have two BJT, then we call it as the cascade. Or BJT with the FET, also we can call it as the cascade. Okay, this one is the second assumption. The internal resistance of the power supply assumed to be zero, such that the voltage drop due to AC is treated as the ground voltage. So for the voltage source, we assume that connect to the ground. Then the AC reactance of internal capacitor is very large, then we consider as open circuit for AC analysis. Okay. We have the phi model and the T model. These two we call it as the RE model, and proven to be useful for analyzing for the AC voltage gain in the AC analysis. Okay. Because of the hybrid equivalent model may or may not be the actual operating conditions of the amplifier. So for the hybrid parameter of the transistor, normal specified at the operating conditions, such as if we have the collector current, this is the value. Or this one is if we use the BJT. Okay, and voltage to emitter VCE. Okay, this is the value as we you have to measure in the experiment last week. Okay, this one is collector current is the IC. Okay, collector current IC, voltage to emitter collector to emitter voltage is VCE. Okay. For the hybrid equivalent model, we consider this one an amplifier with two-port network. We have the input. This one is the input port. This is the output port. Okay, so for the analysis, this one is where we will measure on the C in. This is for the C out. Okay, V in. This is V out, and AV equals to V out over V in. If here we have AI, this is I naught, II. AI equals to I naught over I in. Okay, voltage at the output over voltage at the input for the voltage gain. This one, current at the output over current at the input for the current gain. Okay, and this is these two due to the voltage and current, the hydric equations that we can get from this V in, I in, V out, and out, I out. Okay. For here, for these two equations, when V naught is shorted, we only have this one, H11 and H21, meaning this is equals V naught equals to 0. And then when at the output port is open, when open, I equals to 0. When I equals to 0, we only will have these two parameters. Okay, H12 and H22. Okay, let's see on the circuit. This one is, we can get, actually this is for the derivative, how to get this small signal model by using Norton and Thevenin's theorem actually. Okay, the typical value of Rx here for the good transistor shall be in the regions of 10 to the power of -4, very small value. Thus, the voltage source HVX V0 can be assumed 0 in most circumstances. So, because of the small value. Okay, and we know that from Ohm's law, V equals to IR, and I equals to V over R equals to V0 over 1 over HOX. This one. Okay. For this one is I naught. Alright. So this one is for hydro equivalent model for common source. We have gate, source, and drain. For common source, we consider at the source connect to the ground. Okay. So we have the HIS here is equals to RGS. Okay, we have the HFS. IS is equals to GMVGS. GMVGS. HIS is RGS. And what else? 1 over HOS is the output impedance, R naught. And okay, that's all. Okay, this is AC hydric file model. And this is the voltage gain, the AC voltage gain. Okay, so we have the gate, drain, and this is the whole node for source. Okay, hydric file model of FET AC equivalent circuit, and this is the simplified version. Okay, so from here we know that this is the input, this is output, and input is in here at this node. This is input. Okay, and from here we know that V in is equals to VGS, same node, because this is for V in. Okay, V in plus minus, so equals to VGS. And from this part, V out is equals to, V out equals to minus GM VGS R naught. So if we have R naught here, so why minus? Because for the V out, the I naught we assume to be at this direction, because V out is plus minus. So the current is flow this way. That is why we take this current source up, down. Okay, for the in opposite direction, so we put it minus GMVGS R naught. So for the AV equals to V out over V in. Okay, this V out, I want to change my pen. V out is this value and V in is this value. So we can get this minus GMR naught. You can cancel minus GMR naught. Okay, And the RGS in this circuit is the gate source resistance, and R naught is the output impedance. If RGS is assumed to be infinitely large and R naught is large enough to be neglected, these two considered as open circuit. That is why for the simplified version circuit, there is no RGS, this one, and also no R naught. Okay, if we consider RGS and R naught is very large value. Okay, depend on the question. Sometimes if the questions mention with the value of RGS and R naught, then you should put the value in the circuit. Okay, this is the ACT model of JFET or MOSFET AC equivalent circuit. Okay, for the RE is derived at this site. R in source, okay, derived based on the fact that AC source resistance are in source VGS over IS. Okay, and for V in is equals to 1 over GM multiplied with the IS. For this is the AC source resistance, and IS is equals to GM VGS. Why? Because the IG is equals to 0 for the FET. So for ID equals to IS. And we know that V in is equals to VGS. V in at this node. So we have the V out equals to minus GM VGS R naught. V out is at this spot. Okay. Alright. So next one, we go for the JFET small signal amplifier. Okay, we have the DC parameter for JFET. Just now is for FET. Okay, and various configurations, common source, common gain, and common gate. Okay, and this is for AC equivalent model. And we want to measure for the AC voltage gain. Okay, for the AC 5 model and ACT model, we have the effect of output resistance. Output resistance is the R naught. Okay, and then we have the source resistance. Source resistance is the RGS. Okay, similarly, the amplifications can be achieved for P channel and also for N channel. Okay, but then this one here is for amplifications of N channel, but then it is in the same operations. Okay, the first graph here, this is for transfer characteristic curve of N-channel JFET showing the signal amplifications. Consider this is the input and this will be the output. From opposite, this one is from a different side of phase. Okay, a small change of gate to source voltage, which is the VGS, can result in the large change in drain current. This is VGS and this is for the drain current. Okay, and for this second graph here, the drain curve of N-channel JFET showing the signal amplifications. We have the at the Q point. Q point is the operating optimum point for VCSQ, VDSQ, and IDQ. The change will also show in the drain to source voltage in the VDSQ. Okay. And this is DC analysis of the JFET. We have the DC transconductance, so the GM for transconductance in DC. Okay, for these expressions. This is from this graph. Okay, and the triangle here is the changes. Okay, the delta. And for AC transconductance for GM, we take the value of ID over the VGS. Okay, and ID is equals to GM VGS from here. Okay. Now we go to the AC equivalent circuit. Okay, the hybrid foil model or the RE model. Alright, so this is the AC equivalent foil model of JFET. Can be drawn like this for the MOSFET AC equivalent circuit. Okay, just now we know that ID is equals to GMVGS. Okay, and this is the simplified version. Okay, this one. We have the R naught here. R naught is equals to VM plus VDS over ID. Approximate to VM over ID. Okay, what is VM? VM is the early voltage value. Okay, and R naught is the output impedance. RGS here is the source to gate resistance. Okay, and how to get this simplified version circuit? Okay, the second circuit here, if we consider RGS is very large and R naught is also infinitely large, then we can neglect these two resistance in the circuit. That is why in the second circuit we don't have the RGS and R naught. Okay. Next one is on the T model of JFET or MOSFET for AC equivalent circuit with the R in source. R in source is from this side.
Miss, you unmute. We cannot hear you.
Now can you hear?
Yes, yes.
Okay. Dari awal ke tak dengar?
No, just 2-3 minutes lah.
Okay. Alright, kat mana tadi yang tak dengar tu? Which slide?
From that.
Here.
Effect. No,
Okay.
no.
This one, can we go back? Okay, DC. Okay, for here lah. Yeah, okay. Alright, so this one from here. Okay, for DC analysis of JFET, small signal amplifier. Okay, this is the two graph for showing for amplification. Okay, for amplification. This one is for N channel, but then actually we also can have this one for P channel. It is the same amplifications can be achieved for P channel as well. So we have this one, we call it as the transfer characteristic curve of if N channel, then of N channel JFET. Okay, for the amplifications, we have the ID and VDS for JFET. Okay, and if you can see here, this is in opposite phase. This one for the ID and for the VGS. Okay, for if we have a small change of gate to source voltage VGS can result in large change in drain current or ID. Okay, and this change also show in the drain to source voltage because for here, for this second graph, we have the VDS. Okay, the drain curve of N-channel JFET showing the signal amplification as well. Okay, this is for DC transconductance. Okay, the GM for DC and AC. If for DC, the delta here is the changes in ID over the changes of VGS. Okay, for AC, this is the value for ID over VGS. And from these expressions, we can get the ID equals to GM VGS. Okay, ID is equals to GMVGS. Okay, and let's see the RGS and R naught. RGS is a value gate offset source resistance, and R naught is the output resistance. VM is the early voltage. Okay, this is the second circuit here. This one, this is first, and this is the second. Second circuit is the simplified version. Okay, how to get this simplified version? We have the RGS and R not in the circuit at the first circuit. But then if we consider the value of RGS and R not is infinitely large or large enough to be neglected, so that is why we can get this simplified circuit, the circuit number 2, with no RGS and R not. Okay, only if the question mentioned about the RGS and R naught is infinitely large and we can neglect. If the question gives the value for these two, then you should put the value and consider in the calculations. Okay. This is to get for the R in source. R in source is actually from this when we look at this part V in. Okay, this is V in. V in is equals to VGS and IG is equals to 0. So there is no I in here. ID is equals to IS. Okay, this is IS. Okay, this is the T model of JFET, or also we can use this circuit for MOSFET AC equivalent as well. Okay, and this one is for voltage gain. Voltage gain is AV equals to V out over V in. Okay, V out over V in, and for V out over V in, this is for V out IDRD over IDGM, the V in. So we can cancel this ID and the GM naik ke atas, get minus GMRD. Minus is because the I at the output port is in opposite direction. Okay, so that is why we have the minus. Okay, not to worry on the value of the minus, only showing on the different phase or different polarity. It is in the same magnitude value. Okay, this is for voltage gain. We have the self bias JFET small signal amplifier with the AC equivalent circuit. Okay, let's see here. We have the C1 in the DC circuit. We have C2. Okay, we have C1 and C2. But then for this AC equivalent circuit, there is no resistor because no capacitor, because the capacitor will consider short circuit. Okay, short circuit this one and short circuit this one. If we short circuit the C1, so the VG will connect to V in. So this one, okay, dia putus kat sini. Okay, connect to V in. We have the RG, yes, we put the RG. Okay, so this is for the same as the BJT. This is for the AC equivalent for the transistor. Then we connect with the what else that we have in the circuit. Okay, from D, connect to RD. Okay, connect to RD. And from RG, we have the RG. And then drain. This is drain, gate, source. For source, we have the RS. But then for this AC equivalent circuit, there is no RS. Why? Okay, because now we have the C2. Okay, it's short here. When it's short here, the current will flow. Current nak lalu mana? Nak lalu RS yang ada resistance or the path with no resistance? Okay, straight away the current will flow this path lah. Buat apa dia nak lalu path yang ada resistance? Okay, so consider this one is open circuit. Okay, because we short this one, there is no RS. That is why for the AC equivalent circuit, no RS. Okay, basic concept of current. When there is two paths, one with the resistance and the other path is no resistance, current will flow by the path with no resistance lah. Okay, and one more thing I want to highlight here, why at this source, sini, this is source kan, IS, and ID is kat sini lah, because this one is drain. But then for here, the ID at the source is dia tulis IS. Why? Because IG is equals to 0. Kat sini, IG is equals to 0. So ID is equals to IS. Okay, from atas dia flow straight to the bawah. Dia tak pecah at the gate. Okay, that is why IG is equals to IS, because ID equals to IS because IG is equals to 0. Okay. Alright. What else in here? For AC equivalent circuit, okay, V out from this one. V out is equals to minus VDS. Okay, equals to minus IDRD. Minus because V out is we assume the current is this way. But then we have the current source ke sini. So that is why we take the negative. Okay, V out positive and negative. So current dia mesti dari atas ke bawah, positive to negative. Okay, that one is for V out. For V in, kat sini, V in is equals to VGS. Same note. So it is the VGS equals to VGS ID over GM. Okay, for VGS. This one, ID equals to GM VGS. So we want to get the VGS, so ID over GM. And then for the AV equals to V out over V in. And then kita masukkan lah. Minus ID R naught over ID over GM. So we can cancel, equals to minus GM RD for AV voltage gain. Okay, for voltage gain. Okay, so now here, this one if we have the circuit with R naught impedance. Tadi tak ada, this one we have the output impedance kat sini. So this will be the expressions for voltage gain with the output impedance. We parallel these two. So this is actually parallel. RD parallel with R naught. This is formula for parallel resistance. Okay. Okay, this is if we have the R naught and RS resistance. Okay, when we remove the C2, the source resistance RS, we can get the RS. RS, where is the locations? Kat sini. Okay. If there is no C2, tak ada kat sini, so straight away RS will be appear in the AC equivalent circuit. This one, dia duduk dekat bawah. Okay, from source. Source connect with the RS. So this will be the expressions of the voltage gain if we have the RS in the circuit. RS at the source. Okay, and voltage gain is reduced further for this one because V in is not equal to VGS. Okay. For here, V in, it is not equal to VGS because VGS from this point only. So we have the RG dekat bawah. So V in is equals to VGS plus GM VGS RS. So you can take out the, oh sorry, this one is VGS. You can take out the VGS, factorize the VGS, mau jadi VGS bracket 1 plus GMRS. Okay, and for this VR equals to minus GM VGS R out parallel with the RD. Parallel these two. Okay. Now let's see for the common source. For common source, okay, or common drain amplifier. Sorry, common source is actually for sorry, this one. Common source amplifier because the source is connect to the ground. Okay, and this is the common source JFET circuit 1. Common source JFET. Circuit 2 is the AC equivalent for common source. If the DC circuit is biased at midpoint, then we have the ID equals to IDSS over 2. And then since this one is self-biased, so we can get the VGS equals to minus IDRS. Okay, for this AC equivalent circuit, okay, there is no C1, C2, and C3 because this C1, C2, and C3 is considered short circuit. So connect straight away from here, this one and this one. That is why there is no RS. Okay, the current will flow from here. Okay, and the V0, V out voltage source and V in consider open circuit. Okay, open circuit, there is no these two. Okay, let's see on the, this is for common source amplifier for ID, drain current. Okay, and we have the R in gate and this is for voltage gain, AV equals to V out over V in. And what we have here, IDSS. IDSS is the drain reverse current and IGSS is the gate reverse current. Okay. Next one, we have the common drain amplifier. For common drain, the drain is connect to the ground. This one. From the drain, it is goes to the ground. Drain gate source because from the drain we consider the current source, voltage source is connect to the ground, so that is why this is ground. The D goes to ground. VGS is from this node 2 and this is V in. Okay, from this node. This is short here, short for here. Okay. Okay, the input impedance of the gate R in is very high, then it can be calculated from the gate reverse current IGSS value for a specific VGS. So this is the parameter for the common drain amplifier. IDSS, drain reverse current, and for the IGSS, gate reverse current. For the, this one is voltage gain. Okay. Next, we have the common gate amplifier. For common gate, gate is connected to the ground. Okay, this one. Due to C2, there is no RG. But then we have the RS at the input. We have RD. This consider open circuit. This is connect to ground. Okay, RD goes to ground. And then for this one, replace with this equivalent circuit. Okay, let's see on the expressions. This one, IDSS, drain current. This is IDSS, the drain current maximum at pinch off at VGS equals to 0. And for IGSS, gate reverse current, we have the VGS off here. This one is the cut-off voltage gate to source. Okay, and this is for voltage gain for common gate amplifier. Alright, so next one is MOSFET small signal amplifier. Just now we discussed on the FET. Now we go for MOSFET. Okay, study on the small signal amplifier design with MOSFET, the DC characteristic and DC parameter, and also for AC equivalent circuit, we have the common source and common drain feedback, and also we can have on the uh, two-stage of amplifier for two stages. MOSFET, it can be MOSFET plus the BJT. Okay, let's see for the DC analysis first. This is the explanations for this one actually. For DC analysis of MOSFET. Transfer characteristic curve for depletions enhancement MOSFET. Okay, depletions enhancement MOSFET. This is the names for the MOSFET lah. And now, as you guys can see here, for the transfer characteristic curve, we have the Q point. Okay, we have the Q point, or it is the maximum point. Okay, and the drain current, this is the drain current equations, the ID, the equations for the transfer characteristic curve of depletions enhancement MOSFET. And VGS off is the cut-off voltage gate to source. Okay, and normally for this value of IDSS will be given. What we have here is the L is length of channel length. W is the width of the gate, and COX is the capacitance of outside, and we have mu n is effective mobility of electron for n type. If it is for p type, we have the mu p, effective mobility of the hole. Okay. And the transfer characteristic curve of enhancement MOSFET, this one, okay, enhancement MOSFET, and the Q point of E MOSFET cannot be laid on drain current. Just now, the Q point is at this drain current axis. But for this enhancement MOSFET, it cannot be laid on drain current axis because the MOSFET requires a minimum VGS voltage to operate, which is termed as threshold voltage or VGS threshold, to switch on the device for a normal operation. And the Q point is normally set at the linear part of the curve to avoid non-linear distortion. So this is the part where we consider it is linear curve. Oh, sorry, this one. Okay. Okay, let's see on these expressions for the drain current. This is at linear region. And this one is at saturation operation region. And the K is for transconductance parameter. Same goes. This one is the transconductance parameter. Normally the value will be given. Okay. All right. This is the explanations for this DC analysis for IV characteristic curve of N-channel region. Okay, we have the triode region, saturation region, and the cut-off region, the three regions. Okay, this is for typical IDVGS characteristic curve of N-channel MOSFET for the selected VGS. Okay, we have three regions, cut-off, triode. The triode region This one is almost linear because it is considered as increasing. Okay, and the saturation is the operation region. And saturation region is the useful region for an amplifier operations, whereas for the other regions, triode or the cutoff is good for switching. Okay, this is considered as on. This is for off region. Okay, off condition. Okay, for output impedance of the MOSFET, this is for fixed VGS voltage after neglecting the small VDS value. This is for the output impedance. Let's see. Okay, this is for output impedance of the MOSFET. Okay, illustrates how the early voltage Vm can be determined. Okay, we assume from the IV characteristic, okay, and the lambda is 1 over Vm. Vm is the early voltage, normally range from 20 Vm, 20 to 200 voltage. And this is for cut-off region. Okay. Okay, practically there is no gate to source current. IGS equals to 0. Okay, and because of gate to source resistance, our in gate is extremely high, very large value, and considered as open circuit. That is why there is no value for IGS. Okay, let's see on the circuit. Okay, this is assumptions of R naught is equals to infinity. So here we have the assumptions of the R naught. Okay, two common source AC circuit of MOSFET small signal amplifier, which are the most common and useful AC circuit used for determining the small signal AC voltage gain. Okay, the first one is the MOSFET equivalent circuit using transconductance formula. Okay, here. Okay, with the R, without the R naught, this one is with the R naught. Okay, and the analysis for the MOSFET is the same as the JFET for the voltage gain, especially. And this is for common source amplifier. Okay, analysis is the same as the JFET. We have the C1 capacitor, C2 capacitor with the drain, gate, and the source. Okay, source is connected to the ground. Okay, for this one is for the DC analysis for VGS, gate to source voltage, and this is for drain current with the transconductance value. All right, so this is the AC analysis, AC circuit of a common source. Okay, this is where we will have to measure for the R out input output impedance. This is okay. This is for R in. Okay, and if we look at from here, R in is equals to R1 parallel with R2. And for R out is equals to R naught parallel with RD. Okay. And for V out is equals to this voltage current source but in opposite directions multiply with this R naught. Okay, and from this side V in is equals to VGS. Okay, so this is the expressions. Just now I mentioned R in is equals to R1 parallel R2. R naught is small R naught parallel with the RD. V out is the current source in opposite directions multiply with the R out. Okay, and then V in is equals to this one. AV equals to V out over V in. Okay, so we have the voltage gain here. Alright, so the second circuit is the drain feedback MOSFET. Okay, The drain current we can calculate from this is the expressions for the drain current. From here, from the drain current, we can get the VDS. Okay, since there is no IG or IGS, okay, and the IG is equals to 0, so the voltage across drain and gate also must be 0. Okay, for at saturation, this one, VGS is equals to VGS threshold. Okay, this is the AC equivalent circuit for drain feedback amplifier, or this one is also we call it as the common source if it is in for FET. Common source is connect to the ground. Okay, and this is for R out. Okay, for the R out, this is all the expressions actually. R out is early voltage over ID. AV, we get this one. Why we have RL? Because in the circuit we have the RL. Okay, we have RL. Okay, and from here we know that V in is equals to VGS. And input impedance V in over I, this one. And if we have the Miller's effect, so this one is equals to the Miller's input resistance for this expression. Okay, this one is if we have more than one stage amplifier. Okay, meaning that in the circuit we have two transistors. Okay, for example, this one multi-stage amplifier, we have the we call this one as the BMOS amplifier because we have the BJT with the MOSFET. MOSFET is at the first stage, BJT at the second stage. This one is the cascaded BMOS amplifier circuit. Okay, this one. This is first stage, this is the second stage. So for the analysis, we can do for DC and AC analysis as well, but then must take into consideration for these two transistors. Okay, for the gate voltage of N channel amplifier, for the first one we have the MOSFET. Okay, so for the first stage for MOSFET, this one is for VG, and then we have the VS and we have the VGS. This is for the first stage. And this one is for second stage. Okay, second stage for BJT, we have the VB, VE, and IE. This is all the parameter for BJT. Whereas this one is all the parameter for MOSFET. Okay. Other than that, we also have the AC analysis for both stages as well. Okay. But then for the AC analysis for AV total is equals to AV1 multiplied with AV2. AV2. AV1 multiplied with the AV2. Okay, the voltage gain of first stage N channel MOSFET is minus GMRD, and the GM transconductance, GM is equals to the delta ID over delta VGS. However, due to the we have the loading effect, okay, then we can have these expressions for the first MOSFET. This one is the for second BJT, and this is will be the overall voltage gain due to first stage and second stage. Okay, why we design for multi-stage amplifier? Because it is depends on the purpose for the amplifier itself. Okay, since for the MOSFET or JFET and BJT have different characteristics. Okay, next one we go to frequency response. Okay, what is frequency response? And it is actually frequency range versus the amplitude. Okay. Okay, let's go to the introduction. Okay, the voltage gain of amplifier is the functions of input signal which is dependent on the magnitude and frequency. Okay, effect of the AC voltage gain of amplifier can be significant at low frequency operations, and the effect of capacitive reactance of coupling and bypass capacitor, also with the internal capacitance of the transistor to the AC voltage gain of amplifier is assumed to be zero at mid-range frequency. And that is why it is do not have any effect to the AC voltage gain. Okay, figure below, let's see. Okay, this is a figure of amplifier gain versus frequency. Okay, response of AC voltage gain of an amplifier with the frequency of input signal. Okay, we can divide it into low frequency range, this one. Okay, this is for mid frequency range and this is for high frequency range. Okay, FH is the high critical frequency, whereas for give effect on the high frequency begins to significant. Okay, FL is the low critical frequency, where for the effect of low frequency begin to be significant. Okay, now we want to observe on the effect of the capacitance, okay, in terms of the frequency. This is a typical capacitive coupled JFET type amplifier with the JFET transistor, and we have capacitor C1, capacitor C2 and C3. C3 is the bypass capacitor, C1 and C2 is the coupling capacitor for input. This is input and this is for output port. Okay, for the effect of capacitance, the voltage gain at low frequency is lower because the reactance contributions of capacitor is large. Okay, but then it is opposite for high frequency. Okay, we have C1 in series with RG and RSS and C3 parallel with the RS in the circuit. Okay, as the frequency decreases, the effect is higher. Okay, C3 and C2 also act as high pass filter element. Okay, and at low frequency, the internal capacitance of JFET or MOSFET also true for, let's say if we use BJT, okay, for internal capacitance appear to be open circuit. Okay, for the bypass and coupling capacitors have values in the microfarad range, very small value. Okay, and at high frequency, this capacitor appear to be short. Okay, to understand the effect of high frequency to the gain of an amplifier, we need to know the internal capacitive components for either JFET, MOSFET, transistor. The internal capacitance of JFET or MOSFET transistor basically from the gate insulation layer of the device. Okay, so this is types of internal capacitor for the JFET. Okay, where is the locations? This one. Okay, CDS in between drain to source. CGD between gate to drain. And CGS between gain to source. Okay, the internal capacitance have magnitude in picofarad to nanofarad. Okay, and this appear to be open circuit at low frequency. Okay, it is an opposite as the coupling capacitance. Okay, let's see on the figure. Okay, this one. Okay, this is the internal capacitance of device with the effects of internal capacitance to the frequency. The magnitude of capacitance between drain to source CDS is around 2 orders smaller than CGS and CGD. That is why it is considered as insignificant. Okay, CDS kat sini. Okay, so insignificant, we are not going to consider on that. Okay, this is the AC equivalent circuit showing the effect of capacitance of CGS and CGD. Okay. Okay, now we have to take considerations on the CGD and CDS. So in dealing with high frequency response where internal capacitance is important, then we should use the Miller's theorem to simply the analysis due to the CGD for the JFET and MOSFET. So we have the C in Miller and C out Miller. Okay, this is for C in Miller and for the input side. C out Miller for the output side. C out is the output internal capacitance, okay, which either CBC or CGD. Okay, let's see on the, okay, this is the circuit. Okay, as you guys can see, the capacitance CGD has greater impact on input capacitance than its actual value since it has 1 plus AV factor. Okay, CGD this one at input. As for the output side, this one has the effective output capacitance is approximately equal to CGD because 1 plus AV over AV is approximate to value 1. Okay, close to 1 for high voltage gain AV. Okay, this is for input and this one is for output. Okay, now we go for the critical frequency and phase. Okay, this is for low frequency RC network of input due to the capacitor C and the resistance. Capacitor C and all the resistance that we have. So the R is equals to RS. These two is in parallel. R1 parallel with R2. So consider as all in series. RS in series with two parallel. Okay, R1 and R2. Okay, this is for critical frequency for V out and V in. And this is for minus 3 dB gain. Okay. Okay, minus 3 dB gain. When frequency F is equals to Fc at this point where the resistance R is also equal to capacitive reactance at C1 over omega C. Okay, and this 0.707 meaning that the transfer functions Vg over Vin is attenuated to 70% of the input signal Vin, or if in decibel equal to minus 3 dB. Okay, so this one is for the minus 3 dB gain. As we have conduct in the experiment last week. Okay, let's see on the critical frequency and phase. Okay, this is expressions for in the S domain analysis. RC is also defined as the time constant or the tau. And this one yang bawah ni is the dot plot of low frequency response. Okay, how to read on this dot plot? Okay, if the Vg is 1/10 of input signal V in, then the signal output V out is attenuated by minus 20 dB. Also implies that frequency is equals to 0.1 Fc. Okay, if the Vg is 100 of the V in, then V naught is attenuated by the minus 40 dB, implies at frequency equals to 0.01 Fc. Okay. This is for low frequency. And this one is the Norton and Thevenin equivalent circuit for RC network with the capacitor and the resistor circuit. Okay, and RC network with the bypass capacitor C parallel with the resistance R and a current source I. Okay, let's see on the high frequency. This one for the high frequency. Okay, if the V naught is 1/10 of the input signal IR, then the signal at V naught is attenuated by minus 20 dB. Also implies at the frequency F equals to 10 Fc. Minus 20 at 10 Fc, known as minus 20 dB per decade. If the V naught is 100 of the input signal, then the output signal is attenuated by minus 40 dB, implies at 100 Fc to get this one. Okay, so this is at high frequency response. This is the dot plot of high frequency response. Okay, this is for common source FET amplifier circuit with 2 RC network. This is the first one and this is for the second one. Okay, one of the input, one at the output. In the mid-range frequency, AC voltage gain is equal to, for this one, AV equals to minus GM RD parallel with the RL over RD plus the RL. Okay, for this circuit. And this is the input RC network of the common source amplifier. We have the, okay, this is the expression just now for the voltage gain. This is for output of the RC network. Just now is input. This is for output due to the capacitor C2. For the input due to capacitor C1. This is due to capacitor C1. This is due to capacitor C2. And expressing in decibel, the AC voltage gain AV in decibel with the account by two external capacitor C2 and C1. So we have this 20 log in decibel. Okay, and this is for high frequency of JFET with the C in Miller and C out Miller. Okay, when we apply the Miller's theorem to the amplifier circuit to obtain the C in Miller and the C out Miller. Okay, and this is the equivalent circuit with the, this one is with the C in Miller. Do we have next one with the C out? Okay, this is at the output with the C out Miller. For high frequency at output for C out Miller. Okay, this is high frequency for input. Okay. I want to show one more circuit. Okay, this is common source MOSFET amplifier circuit. Okay, small signal amplifier with the, we have C1, C2 and C3. Okay, for common source. Okay, this is for low frequency for here. AC circuit of the amplifier with the assumption that the gate resistance R in gate is very large, then we can treat it as open. And this is the voltage gain expressions for mid-range frequency AC voltage gain with the RD and RL in parallel here. Okay. It is due to the capacitor C2 and C3 of the critical frequency in the RC network. And this is for low frequency, knowing that the low frequency critical frequency of the amplifier circuit, take the 20 log to get the value for decibel. Okay, this is for high frequency AC equivalent circuit. For high frequency, we must take the considerations for the C in Miller for input and C out Miller at the output. Okay, this is the expressions for high frequency small signal AC voltage gain in decibel. knowing that high frequency, critical frequency of the amplifier circuit 20 log in decibel for the voltage gain. Okay, this one, if we have the multi-stage amplifier, it can be more than one stage. Okay, and when two or more stage amplifier are cascaded to form multi-stage amplifier for obtaining high gain and bandwidth, the overall frequency response is determined by the frequency response of each of the stages. Okay, depending on relationship of the frequency. Okay, then for angular 3 dB frequency of this amplifier stages. Okay. This is slightly lari ni. Nanti I will betulkan and I will share the notes again. Okay. Alright. So that's all for the the FET transistor circuit. We have covered for the FET and for the MOSFET as well for single stages and for the cascaded and multi stages. Okay, is there any question from you guys? Is there any question?